And we're going to spend the rest of the class today talking about each of these and then give an example of a proof. We'll start with propositions. A proposition is a statement that is either true or false. You may not know which one, but it's one or the other. Simple example, 2 plus 3 equals 5. Now, that's a true proposition. Here's one that's a little more interesting. For all n in the set of natural numbers, n squared plus n plus 41 is a prime number. All right, now I've used some notation here. This is, the upside down A is the for all symbol. How many people have not seen that symbol before? All right, a bunch of you. Yeah, you're going to see a bunch of symbols here first week. And that means for every possible choice of n, and this is in the natural numbers, which is the set 0, 1, 2, 3, and so forth. It's the natural numbers. It's basically the integers, but not negative. So we're saying for every natural number, i.e. for 0, for 1, for 2, and for 3, and so forth, this expression is a prime. Now, a prime number is a number that is not divisible by any other number besides itself and 1. So 2, 3, 5, 7 are prime. 9 is not because it's 3 times 3. Now, this part here is called the predicate. And a predicate is a proposition whose truth depends on the value of a variable. In this case, n. All right, this is referred to as the universe of discourse. It's the space of all things we're talking about. We're only talking about natural numbers here. This is called a quantifier. We'll see more quantifiers later. All right, now to see if this proposition is true, we need to make sure that this predicate is true for every natural number n. So let's see if we can check that. Let's try some values. So we'll try n is 1, 2, 3, and so forth. And we'll compute n squared plus n plus 41. And then we'll check, is it prime? So for n equals 0, n squared plus n plus 41 is 41. Is 41 prime? Yeah. Nothing divides 41 but itself and 1. All right, let's try 1. 1 squared plus 1 plus 41 is 43. Is 43 prime? Yes. Let's try 2. We get 4 plus 2 is 6 plus 41 is 47. Is 47 prime?
Yes.
Yes. Looking good. 3, I got 9, 12, 53. 53 prime? Yes. Yeah. And I could keep on going here. I could go down to 20. I get 420, 461. In fact, that is a prime. And I could just keep on going here. Go down to 39. I get 1601. You can check that as a prime. The first 40 values of n, the proposition is true. The predicate is true. It is prime. Now, this is a great example because in a lot of fields, physics, for example, statistics often, you know, if it's true, you checked 40 examples. That's above and beyond the call of duty. It's always true. So yeah, this must be true, right? No, wrong. Often you'll see this in a lot of scientific fields. It is not true. Can anybody give me an example of n for which n squared plus n plus 41 is not prime? Yeah. 40. Good. Let's see about 40. 40 squared plus 40 plus 41 is 1681. What's that equal? 41 squared. So it is not prime. Somebody give me an obvious example where it's not prime. 41. Yeah, 41 squared. Everything is divided by 41. But 40 is the first breakpoint. So the first 40 examples work, and then it fails. So this proposition is false, even though it was looking pretty good. There's a reason I'm doing this. In fact, I'm going to do it some more here. I'm going to beat you over the head with it. Here's a famous in mathematics statement. A to the fourth plus b to the fourth plus c to the fourth equals d to the fourth has no positive integer solutions. That is a proposition. Now, this proposition was conjectured to be true by Euler in 1769. Euler's a big honcho in math. You know, we still talk about him a lot, even though he's been dead for centuries. It was unsolved for over 2 centuries. Mathematicians worked on it. It was finally disproved by a very clever fellow named Noam Elkies. 218 years later, after it was conjectured. He works at that other school down the street. And he came up with this. A equals 95,800. B equals 217,519. C equals 414,560. You don't have to remember these numbers. We're not going to quiz you on that. 422,481. Now, he claims, I've never personally checked it, but presumably people have, you plug those in here, and you have an equality. So he says. So in fact, the correct true proposition is there do exist A, B, C, D in the positive natural numbers such that A to the fourth plus B to the fourth plus C to the fourth equals D to the fourth. All right, I used a new quantifier here called there exists. Instead of an upside down A, it's a backwards E. Don't ask me why. That's what it is. The plus means you can't have 0 or negative numbers, so these are the positive natural numbers. And here's your predicate, which, of course, the truth of this depends on the values of A, B, C, and D. All right, it took a long time to figure out that actually there was a solution here. Obviously, everything they tried till that time failed. Let me give you another one. (313) x cubed plus y cubed equals z cubed has no positive integer solutions. This turns out to be false, but the shortest, smallest counterexample has over 1,000 digits. This one was easy. They only have 6 digits. So there's no way ever you'd use a computer to exhaustively search 1,000-digit numbers here to show it's false. Now, of course, some of you are probably thinking, why on earth would I care if 313 times x cubed plus y cubed equals z cubed has a solution? Now, that probably won't be the last time that thought occurs to you during the term. And why on earth would anybody ever try to even find a solution to that? You know, I mean, mathematicians are sort of a rare breed. Now, actually, in this case, that's really important in practice. Okay? This equation is an example of what's called an elliptic curve. Elliptic curve, and you study these if you're really a specialist in mathematics in graduate school, or if you work for certain 3-letter agencies. because it's central to the understanding of how to factor large integers. That means, factoring, showing that, what was it? 1681 is 41 times 41. And I say, OK, who cares about factoring? Well, factoring is the way to break crypto systems like RSA, which are used for everything that we do electronically today. You have a PayPal account, you buy something online, you're using SSL. They're all using crypto systems, almost all of which are based on number theory. And in particular, they're based on factoring. And if you can find good solutions to things like this, or solutions to things like this, all of a sudden you can get an angle and a wedge on factoring. And it's because of that now RSA uses 1,000-digit moduluses instead of 100-digit moduluses like they used to use, because people figured out how to factor them, how to break the crypto system. If you can break those crypto systems, well, you can't rule the world, but it's close. All right, so we'll talk more about this the week after next when we do number theory and we work up to RSA and how that crypto system works and why factoring is so important. All right, so yeah, you all don't really have to worry about this, but these things are important. And the bigger message is that you don't just try a few cases and if it works, you think it's done. That's not how the game works in mathematics. You can get an idea of maybe it's true, but doesn't tell you the answer. All right, let me give it another one. This is another very famous one that probably most of you have heard of. The regions in any map can be colored in 4 colors so that adjacent regions have different colors. Like a map of the United States, every state gets a color. If 2 states share a border, they have different colors. So you can distinguish them. This is known as the 4-color theorem, and it's very famous in the popular literature. How many people have heard of this theorem before? Yeah, OK, so you've all heard of it. As a long history, it was conjectured by somebody named Guthrie in 1853. He's the first person to say this ought to be possible. And there were many false proofs over the ensuing century. One of the most convincing was a proof using pictures by Kempe in 1879, 26 years later. And this proof was believed for over a decade. Mathematicians thought the proof was right, until another mathematician named Heawood found a fatal flaw in the argument. Now, this proof by Kempe consisted of drawing pictures of what maps have to look like. You start by saying a map has to look like one of these types, and he would draw pictures of them. And then he argued that those types that he drew pictures of, it worked for it. Proofs by picture are often very convincing and very wrong. And I'm going to give you one to start lecture next time. Be proof by PowerPoint, which is even worse than proof by picture. And it is compelling. And the point will be to show you proofs by picture are generally not a good thing, because your brain just locks in, that's what it has to look like. And you don't think about other ways that it might look like. Now, the 4-color theorem was finally proved by Appel and Haken in 1977, but they had to use a computer to check thousands of cases. Now, this was a little disturbing to mathematicians, because how do they know the computer did the right thing? Your colleague writes a proof on the board, you can check it, but how do you know the computer didn't mess up or not do some cases? Now, everybody believes it's true now, but it's unsatisfying. A few years ago, a 12-page human proof was discovered, but it's not been verified. And people are very suspicious of it because the proof of the main lemma says, quote, "Details of this lemma is left to the reader, see figure 7. That's what the main lemma of the proof is. But people think that maybe there were some good ideas there, but very suspicious proof. All right, let's do another one, another proposition, also very famous. Every even integer but 2 actually positive integer but 2, is the sum of 2 primes. For example, 24 is the sum of 11 and 13, which are prime. Anybody know, is this true or false, this proposition? Yeah? Yeah, that's right, me too. Nobody knows if this is true or false. This is called Goldbach's conjecture. It was conjectured by Christian Goldbach in 1742. This is a really simple proposition, and it's amazing it's not known. In fact, I spent a couple of years working on. I thought, oh, well, this has to be easy enough to prove when I was younger, and didn't get very far. So people still don't know if it's true. And in fact, it was listed by the Globe as one of the great unsolved mysteries. So if you get out this Globe article here, one of the handouts. Does everybody have this handout? If you don't, we'll get it passed out. Somebody missing that handout up over there and over here? All right, if we get those passed out. Now it lists the 3 conjectures. Do you see Goldbach's conjecture there? Now, can anybody point out something that's a little disturbing about what the Globe says about Goldbach's conjecture? Yeah, it gives the example, like instead of 24 is 11 plus 13, it says 20 is the sum of 9 and 11. Now, if we're allowed to use things like 9 as primes, Goldbach's conjecture is pretty easy to prove is true. All right, this won't be the last time we get examples from the literature. In fact, we're going to do this a lot along this theme of you cannot believe everything you read. And now the Globe is easy pickings, but we'll do some more interesting ones later. Now this article lists 2 other famous conjectures which most people believe to be true. The Riemann hypothesis, after a 1859 paper written by Bernard Riemann, suggests that zeros in an infinite series of numbers known as a zeta function form along a straight line in the complex plane. The hypothesis has been proved to 1.5 billion zeros. Not far enough to prove it completely. Even if they did 1.5 trillion zeros, it wouldn't be far enough to prove it completely, of course. And then the Poincare, no, actually the Riemann hypothesis a couple of years ago, somebody credible claimed to have proved it. Proof turned out not to be right. Then there's the Poincare conjecture. Now this one was finished off. It was proved to be true in 2003 by a Russian named Grigor Perelman. The conjecture says, roughly speaking, that 3D objects without holes, like not a donut, are equivalent to the sphere. They can sort of be deformed into a sphere. This is known to be true in 4 dimensions and higher, but nobody could prove it for 3 dimensions until Perelman came along. Now there's a bit of a controversy around this guy. He had an 80-page proof, but didn't have all the details. So then other teams of mathematicians got together and wrote 350 pages of details. And then most people believe now that it's right and that his original proof might not have had all the details, but he had the right structure of the proof. So he won prizes for this. He won the highest prize in mathematics, the Fields Medal. And just earlier this year, he was awarded the $1 million Millennium Prize. And there's about 6 problems or so that if you solve one of them, the Clay Institute gives you $1 million. And he's the first one to win the $1 million. Now the guy's a little strange. He rejected the Fields Medal and refused to go to the ceremony where he was being honored. And he's recently rejected the Millennium Prize. And anyway, this area is murky, and we have an expert to explain it all for us on video, which I thought I'd show. All right, let's do a simpler one here. For all n in Z, n greater than or equal to 2 implies n squared greater than or equal to 4. Now Z we use for the integers. And so that would be 0, 1, minus 1, 2, minus 2, and so forth. And this symbol here is implies. All right. In fact, one thing you're going to notice when you read the text is we use different notation there as the standard than I will use in lecture. And there's lots of ways of doing it. You could have a double arrow, a single arrow. You could write out implies every time as it's done in the text. And it doesn't really matter which one you want to use, as long as you use one of the conventions for implies. And let me define what implies means. An implication P implies Q is said to be true if P is false or Q is true, if either one. So we can write this down in terms of a truth table as follows. We have the values of P and Q. Then I'll give the value of P implies Q. If P is Q and Q is true, sorry, P is true and Q is true, what about P implies Q? It's true because Q is true, the definition. If P is true and Q is false, false. P is false, Q is true. True. What about false and false? Is true. Even though this is false, as long as P is false, P implies Q is true. All right? So this is important to remember. False implies anything is true, which is a little strange. There's a famous expression. If pigs could fly, I would be king. Is that true? Sort of. In fact, this statement, pigs fly, implies I'm king. That's true. Because pigs don't fly. Doesn't matter whether or not I'm king, which I'm not. Since pigs don't fly, even though that's false, the implication is true. Now, some of you have worked on these things before, it's second nature. If you haven't, I want to start getting familiar with that. All right, let's do another example. All right, what about this proposition? For all integers, n and z, n greater than or equal to 2, this is if and only if, n squared greater than or equal to 4. Is that true? Is n bigger than 2 if and only if n squared is bigger than 4? It's false. What's an example of n for which that's false? Negative. All right, so it's false. N equals -3. All right? -3 squared is bigger than equal to 4, but -3 is not bigger than equal to 2. And in fact, this if and only if means you have to have an implication both ways. So you got to check both ways for it. So let's do the truth table. Extend this truth table out here. We'll do the truth table for P if and only if Q. All right, so here are P and Q. Is Q implies P true for this row? Does Q imply true? Yeah. False implies true. That's true. True does not imply false. That's false. And false implies false. And so now we can see where P is if and only if Q. If they're both true, then it's true here. What about here? Is P true if and only if Q is true in this case? No, because P implies Q is false, but Q implies P is true. So it's false. False here. I made a mistake there, right? That was true. Oops. Yeah. And true if and only if true. OK, they're both true, so we're OK. So P if and only if Q is true when they're both true or both false. And that's it. If they're different, then it's not true. The key here is to always check both ways. So if you're asked to prove an if and only if, you got to prove that way and that way. All right, we've just done about 15 propositions. Is every sentence a proposition? Yes? No? No. What's an example of something that's not a proposition? A what?
This statement is false.
This statement is false. That's true. Well, that is true. It's not a proposition. Because if it were true, it wouldn't be false. And if it was false, then it would be true and you have a contradiction. So it's neither true nor false. What's a more simple example of something that's not a proposition?
This is a tissue. Definition.
Ooh. Boy, I would have said that's true in some world, you know, because yeah, that's a tissue. So it's a true statement. Hello. That's good. That's neither true nor false. Yeah. A question. Who are you? Neither true nor false. So not everything is a proposition. But this course, pretty much everything we deal with will be a proposition. All right, so that's it for propositions. Any questions on propositions? All right, next we're going to talk about axioms. Now, the good news is that axioms are the same thing, really, as propositions. The only difference is that axioms are propositions that we just assume are true. An axiom is a proposition that is assumed to be true. There's no proof that an axiom is true. You just assume it because you think it's reasonable. In fact, the word axiom comes from Greek. It doesn't mean to be true. It means to think worthy. Something you think is worthy enough to be assumed to be true. Now, a lot of times you'll hear people say, sometimes we'll even say it to you, you know, don't make assumptions when you're doing math. No, that's not true. You have to make assumptions when you do math. Otherwise, you can't do anything, because you've got to start with some axioms. The key in math is to identify what your assumptions are so people can see them. And the idea is that when you do a proof, anybody who agrees with your assumptions or your axioms can follow your proof, and they have to agree with your conclusion. Now, they might disagree with your axioms, in which case they're not going to buy your proof. Now, there are lots of axioms used in math. For example, if A equals B and B equals C, then A equals C. There is no proof of that. But it seems pretty good, and so we just throw it in the bucket of axioms and use it. Now, axioms can be contradictory in different contexts. Here's a good example. In Euclidean geometry, there's a central axiom that says, given a line L and a point P, not on L, there is exactly one line through P parallel to L. You all saw this in geometry. in middle school, right? Got a point in a line. There's exactly one line, another line through the point that's parallel to the line. Now, there's also a field called spherical geometry. And there you have an axiom that contradicts this. It says, given a line L and a point P not on L, there is no line through P parallel to L on the sphere. There's a field called hyperbolic geometry. And there's an axiom that says, given a line L and a point P not on L, there are infinitely many lines through P parallel to L. So how can this be? Does that mean one of these fields is totally bogus, or two of them are? Because they've got contradictory axioms. That's okay. Just whatever field you're in, state your axioms, and they do make sense in their various fields. You know, this is planar geometry, this is on the sphere, and this is on, you know, hyperbolic geometry. They make sense in those contexts. So you can have more or less whatever axioms you want. There are sort of two guiding principles to axioms. Axioms should be, it's called consistent and complete. Now, a set of axioms is consistent if no proposition can be proved to be both true and false. And you can see why that's important. You know, if you spend 3 weeks proving something's true, and the next day somebody proves it's also false, I mean, the whole thing was pointless. So it only makes sense if your axioms as a group are consistent. A set of axioms is said to be complete if it can be used to prove every proposition is either true or false. All right? Now, this is desirable because it means, well, you can solve every problem. All right? Everything is, you can prove it's true or you can prove it's false. You can get to the end. Now, you'd think it shouldn't be too hard to get a set of axioms that satisfies these two basic properties. You're allowed to choose whatever you want, really. Just you don't want to be creating contradictions, and you want a set that's powerful enough that allows you to prove everything is true or false, one of the two. It turned out not to be so easy to do this. And in fact, many logicians spent their careers, famous logicians, trying to find a set of axioms, just one set, that was consistent and complete. In fact, Russell and Whitehead are probably the two most famous. They spent their entire careers doing this, and they never got there. Then one day, this guy named Kurt Gödel showed up. And in the 1930s, he proved it's not possible that there exists any set of axioms that are both consistent and complete. Now, this discovery devastated the field. I mean, it was a huge discovery. You know, imagine poor Russell and Whitehead. They spent their entire careers going after this holy grail. Then Kurt shows up and said, hey, guys, there's no grail. It doesn't exist. And that's a little depressing. Pretty bad day when that happened. Now, it's an amazing result because it says if you want consistency, and that's a must, there will be true facts that you will never be able to prove. We're not going to prove that here. It's proved in a logic course. For example, maybe Goldbach's conjecture is true and it is impossible to prove. Now, we're going to try not to assign any of those problems for homework. And in fact, they do exist. It's complicated. You can state a problem that you can't prove is true or false. And you may be thinking that from time to time. Hey, it's one of those, you know. You remember what your parents told you? If you work hard enough, you can do anything? They were wrong. All right, that's enough for now. We'll do more of this next time.
Father, forgive me, I just saw an angel tonight. In a black dress, brown eyes, Louis V, Westwood on her neck. Westwood on her neck. And Father, I confess, Father, I've done something I regret. She got me with that look in her eyes. Took her back home, I know that I probably should've let it go. Should've let it go, but I let her in my bed. Can you see the horns on her head? 7 days a week, we don't ever get to rest. Blessings on me, giving me a Sunday best. I lost my way, Father, I confess. Father, I confess, she got me possessed. That girl, she looks like an angel, but she's playing with fire. Acts so innocent, but it's all pretend. Worshipping down on my knees, praying she'll show me mercy. Think I see the light, she the one I idolize. Loving her is bad religion. She bad, bad, bad. Yeah, she bad, bad, bad for me. She gon' be the death of me. Temptation captivate me with the way she move her body. Got the Holy Spirit giving me a warning that I shouldn't be messing with a girl like her. I know, but it's too late. Even though I'm well aware there's sin on my plate. She's my forbidden fruit, and I can't help myself. I know it's really right, but that girl's just my type. 7 days a week, we don't ever get a rest. Blessings on me, giving me a Sunday best. I've lost my way, Father, I confess. Father, I confess, she got me possessed. Forsaking my own spirit, I'm ashamed. Burning as I walk into the flame. I know I'm the only one to blame. That girl, she looks like an angel, but she's playing with fire. Acts so innocent, but it's all pretend. Worshiping down on my knees, praying she'll show me mercy. Think I see the light, she the one I idolize. Loving her is bad religion. She bad, bad, bad. She bad, bad, bad for me. She the one I idolize. Loving her is bad religion. She bad, bad, bad. She bad, bad, bad for me.
And so it must be that, in fact, P is not false, namely that it's true. Now, this works because if you can prove if not P implies false is true, well, from last time, the only way this is a true statement is if this is false, namely P is true. All right, so we can conclude that P is true if we can show that not P implies a falsehood. Any questions about that? It's sort of a lot of sort of notation, and until you've seen it, it can be confusing. So maybe we should do an example. Let's prove that square root of 2 is irrational. Is irrational. Okay, everybody knows what an irrational number is? That's something that can't be expressed as the ratio of integers. Okay, and probably most people already know that. How many people have not seen a proof that square root of 2 is irrational before? All right, so most of you have seen a proof of that. Good. You know, if you try to do a direct proof of this, it's pretty hard. How do you show there's no way to represent the square root of 2 as integers a over b? But it's very easy if we do a proof by contradiction. Now, when you're doing a proof by contradiction, always start off by saying by contradiction. Write that down. And then what you do next is you say, I'm going to assume, for the purpose of contradiction, that P is false, namely not P is true. In this case, that would be square root of 2 is rational. So in this case, here's what we're trying to prove. That's P. I'm going to assume not P, namely that square root of 2 is a rational number. Then I'm going to get a contradiction or a falsehood, and then I'm going to know that P was true after all. All right, so let's see where this leads us. Well, if square root of 2 is rational, then we can express it as a over b, where a over b is a fraction in lowest terms. That means a and b have no common divisors. And then I can square both sides, and I get 2 is a squared over b squared. Then I multiply by b squared, and I get 2b squared equals a squared. And what does that imply about a? What can you tell me about a if a squared is 2b squared? Anything special about a? Can a be anything? A squared is even, right? Because 2b squared is an even number, so a squared is even. And what does that mean about a? A is even. If a squared is even, then a is even. So a is even. All right, so we can write that as 2 divides a. That's the divide symbol. You'll see a lot of that next week. All right, if a is even, what do I know about a squared? I know more than just it's even. What is it? It's a multiple of 4, yeah. So that means that 4 divides a squared. A squared is 2b squared, so that means that 4 divides 2b squared. Divide each side by 2 means 2 divides b squared. What does that imply about b? B is even. All right, b is even. Good. Well, I've got a is even and b is even. Have I got a contradiction here somewhere? Yeah, a over b was not a fraction in lowest terms because both a and b are even. All right, so that implies a over b is not in lowest terms. And that gives a contradiction. Now, you'll see that written lots of ways. One is you can say a contradiction. Sometimes you'll see just this sharp symbol written. And that means you got to a contradiction because here we had it being in lowest terms, and here we have it not in lowest terms. You can't have both at the same time. So you got a contradiction. And that means we've now proved that this assumption was wrong. Square root of 2 is not rational, so it must be irrational. All right, and then we put a little box here at the end, or sometimes you'll see a check, sometimes you'll see QED that says the proof's done now. It's over. Any questions about that proof? We're going to do a lot of proofs by contradiction. Actually, there's an interesting story behind this proof. As far as we know, it was first discovered by the Pythagoreans way back when in ancient Greece. And the Pythagoreans were a religious society started by Pythagoras of Pythagoras theorem fame. Now, it sounds weird today, but back then in ancient Greece, math was a religion. All right? Every once in a while, you'll see somebody around MIT and you'll think, he must think math is a religion. But back then, it really was, and it was ruled by gods, because this is ancient Greece. And there were two key gods in this religion, Aperon and Peros. Now, Aperon was the bad god, and he was the god of infinity, because infinity was considered all that was bad. And I don't think we'll do a lot with infinity this term, but if we do, you'll appreciate why that's the case. And Peros was the good god. He was the god of the finite world and represented everything that was good to the ancient Greeks. Now, one of their main axioms or beliefs was that there were no irrational numbers. They just didn't exist. Now, the reason is they didn't like irrational numbers. They were bad because, well, they're infinite. You can't write them as a decimal without repeating forever. And, just an infinite sort of decimal representation. They liked rational numbers, like 1/7. That's a good number because you can write it as 0.142857 repeating. So rational numbers are finite in that you can always find the repeating pattern of finite length. Irrational numbers are not. They're infinite in that sense of the ancient Greeks. So they said there were no irrational numbers. That was an early axiom. Now, they also had an axiom that said that every length of a line was finite, therefore rational. All right, the ancient Greeks were good with the compass and drawing lines and straight edges and stuff. So they said any line that you can construct has a finite length to it, so therefore it has a rational length. That was axiom number 2. Now, they were good geometers, so they knew, of course, they developed the Pythagorean theorem, that if you took a triangle and you had side lengths 1, the length of the hypotenuse was square root 2. Therefore, they had a theorem that said square root 2 was rational, because you got the two axioms there, right? Now, eventually, they discovered a proof like that it wasn't rational. It was irrational. Now, this caused quite a stir. First, it meant that their axioms were inconsistent. Every theorem they'd proved was now suspect once you have inconsistent axioms. Even worse, the devil is in their midst. Square root 2 is infinite, is the bad god, and this is the most basic length they had, besides 1. All right, so that's a very bad thing. Sort of like, today we were to wake up and discover that, there were only 9 commandments, and the 10th was planted there by the devil, and you're not sure which one maybe. That would be a big mess, sacrilege. Well, so what were they to do? This is a disaster of major proportions, so they covered it up, and they denied the result. So they didn't want to publish that proof. So they kept on saying square root 2 was rational. But then, according to legend, there was a deep throat. Somebody who let out the word and the proof that square root 2 was irrational, because that would be very destabilizing for the society. And so they killed him. This is the legend. Now, hard to imagine getting killed over the irrationality of 2, but all right, we're going to do a lot more of these kind of proofs in homework and throughout the term. The next proof I want to show you is one of my favorite proof techniques, one of my favorite proofs, and that is a false proof. And we're going to see a lot of these during the term too. And if we could bring the screens down, somebody back there to, yeah, great. Bring the screens down, and then turn this on for me. So I'm going to prove to you that 90 is bigger than 92. All right, and that hopefully is not really true. But watch this proof and see if you can see any problems with it. All right, the proof by PowerPoint. Right away, you should be suspicious. I'm going to take 2 triangles with total area 90 and put them together and then divide them up into 4 triangles with area greater than 92. And by the conservation of area axiom, which you want to be maybe thinking about, this will imply an area of 90 is larger than an area of 92, and therefore that 90 is bigger than 92. All right, those are my triangles. They are right triangles, 9 by 10. If I put them together, I get a 9 by 10 rectangle. Of course, it has area 90, 9 times 10. Now I'm going to slide these triangles across their diagonal so that I get, instead of having 10 on the side, I'm going to slide it so I get a 2 and an 8. Okay? I had 10 there before, now it's 2 and 8. And then you see I've got this, I kind of cut off along the dotted line. And as you can see, that dotted line, won't compute it exactly, but it's a little bit bigger than 2. Right? It's a little bit longer than that 2 there. You could see that. All right, so I'll call it 2 plus, bigger than 2. Now I slice off along the dotted line. And now I'm going to put those two triangles together, and I create a rectangle, 2 by 2, a little more than 2. Now the area of the little rectangle is bigger than 4, because I got 2 times something bigger than 2. And you can see here I have the 8 left over, and I have 9 plus 2 plus means it's a little bit bigger than 11 by 8. I got area bigger than 88. Add them up. I got area bigger than 92. So I started with 90, and I created more than 92. All right, what's the problem here? I mean, this would be good if I could do it. I'd get some gold, bars of gold and, cut them up and do the game, and I'd make more gold. That would be pretty good if I could do that. Is it the conservation of area axiom? Did I assume something there that was too powerful, that if I manipulate the area of rectangles like this, that the area needs to be the same? Yeah? My bigger ones aren't closed. Well, let's see. I don't know. Let's go back and see how I made those bigger ones. All right, I got my triangles, right? I'm just chopping along the line there, and I got 2 plus and 9. Those are rectangles. They look like rectangles. Yeah, yeah.
2 plus is actually less than 2.
Well, it looks bigger than 2. Doesn't it? Yeah, 2 plus is, well, bigger than 2 is bigger than 2, but yeah, maybe that should have been a 2 minus. Would that change anything? Yeah, if that had been a 2 minus, then we'd have area less than 4, area less than 88, and then 90 would be less than 92. That would be okay. But it sure as heck looks bigger than, the 2 plus looks bigger than the 2, doesn't it? I don't know. Do they got distortion out there? I guarantee you if I measured on my screen, that 2 plus is bigger than the length of the 2. I guarantee you. We can take a ruler on my screen, and the 2 plus will be longer on the ruler than the 2. That I guarantee you, but you're on the right track. Yeah?
That 2 plus is really 1.8.
Good. All right. Now, how did you? But it is true. If I measure it on my screen, it's bigger. Yeah.
So are the triangles like drawn to scale? It's like on
No.
the SAT they always say not to scale, right?
Yeah. Yeah, they're not drawn to scale. In fact, if I go back to the beginning, it says 9 by 10. But in fact, if I measure the 9, it's bigger than the 10. All right? So this is one of the big problems of proofs by picture. Because looking at it, you're not thinking which is bigger, 9 or 10 up there. The 10's bigger, even though it's not. It's shorter. But when you get down into the proof, well, clearly the 2 plus was bigger than the 2, because it looks that way. It is on the paper. All right? In fact, if you go compute it, you're probably right. It's 1.8, not 2 plus. But that's how the error crept in and how it was drawn. And then you're going along with the proof, and everything else is just fine. So the mistake is right up front. I drew it wrong. OK? And this happens, you're doing graph, we'll talk about graph theory in a couple of weeks, over and over again, people do this. They draw it. It looks like this, you accept that, and then you're dead. Everything else, there's no hope. Everybody clear what went wrong in this picture? How we got off track? That's sort of a nasty one. OK. Now, one of the nice things about proofs is that when there is a bug, if you really write it out step by step, and there's a bug, you can go back and find it. And so this, I didn't sort of really write it out very well step by step, and it was harder to find. Now, all right, so if we can pull the screens up. Thanks. OK, so for the rest of today and the rest of this week, we're going to talk about a different kind of proof technique, which is induction. Now, induction is by far the most powerful and commonly used proof technique in computer science. If there's one thing that you should know by the time you're done with this class, it's how to do a proof by induction. In fact, if there's one thing you will know by the time we're done with this class, is how to do a proof by induction. And in some sense, when we get to grading the final, how we measure ourselves as instructors, the first test is, can you do the proof by induction question and do a good proof there? You will see it on the midterm and the final, probably in multiple instances. Now, just to make sure you become intimately familiar with induction, we're going to do over a dozen proofs with induction in class and many more in homework over the next 5 to 6 weeks. You'll probably be dreaming about induction if we're successful here soon. The good news is that induction is very easy. Once you get your mind around it, get some practice, it really is not a hard thing. In fact, induction is really just an axiom. So let me state it. Let Pn be a predicate. If P of 0 is true, and for all natural numbers n, P of n implies P of n plus 1 is true. So here I'm saying that this is true for all n. Okay. Then, for all n natural numbers, P of n is true. All right, another way of saying this without the for alls there is that if P0 is true, if P0 implies P1 is true, if P1 implies P2 is true, and so on forever, then P of n is true for all n. So then P0, P1, P2 forever are true. Okay? Now, you can sort of see why this is a reasonable axiom. Because if P0 is true, and P0 implies P1, then by that modus ponens thing, or one of the logical deductions, we know P1 is true. And if P1 is true, and P1 implies P2 is true, then we know by the same reasoning P2 is true. And so on forever. Now, the reason it becomes an axiom is that and so on forever part of it. That's why we need it as an axiom. You can sort of view this as a series of dominoes. You know, I got a domino for each n. And each domino knocks over the next in terms of truth. Knocking over corresponds to truth here. And if I know P0 is true, that means I knock over P0. P0 implies P1 means P1 goes down. P1 implies P2 means P2 goes down, and so forth. All right, pretty basic. Raise your hand if you think you don't have a lot of experience with induction. All right, yeah, that's pretty typical, about a third to a half of you. So we're gonna change that. Let's do a simple proof using induction. So let's prove that for all n bigger than or equal to 0, again, natural numbers, that 1 plus 2 plus 3 plus n equals n times n plus 1 over 2. This is actually a useful thing to remember. We're going to use this all term, this identity. Now, the first thing, before we prove it, I want to make sure we understand this dot, dot, dot notation, because it is the source of a lot of errors. What it means is that you need to fill in the pattern here. which is vague. What it means in this case is you'd fill in 4, 5, 6, all the way up to n minus 1, and then n. That's what it means. Figure out the pattern and fill it in. Pretty risky thing. Now in this case, because that's so vague, there's other terminology we use for this. For example, we would use a big sigma, capital sigma, I equals 0 to n of I. That means the sum of I, where I is the integers from 0 to n inclusive. Actually, let me put 1 here. Okay. Another way to write this, these are all equivalent ways to write it, is you could put 1 less than equal to I less than equal to n of I. So you could put summing I over the range from 1 to n, or you could write it on the bottom if you want. So these are 4 different ways of writing the same thing, the sum of the natural numbers from 1 to n. And we'll use them all during the term. All right, now there's some special cases that make this a little more interesting. What if n equals 1? I've got 1 plus 2 plus dot, dot, dot plus n. What do you suppose it equals if n equals 1? 1. Because we're summing the numbers from 1 to 1. That's just 1, the number 1. There is no 2. And there aren't 2 copies of 1. So this notation is very ambiguous. You see a 2 here in the sum. If n is 1, you see a 1 here and a 1 here. All right, so you've got to be careful. I guarantee you'll make a mistake with this. In fact, I'm going to show you another false proof later where this comes into play. What about if n is less than or equal to 0? What is it then? Any thoughts? 0. There are no integers to sum. No 1, no 2, no n, because you never get started because you're, sorry, n is less than or equal to 0. Because you're summing from 1 to 0, 0 is below. You never, doesn't include anything. So these are the conventions to keep in mind with the edge cases here. All right, it's easy enough to check that the theorem is true for certain values of n. For example, if n equals 4, I've got 1 plus 2 plus 3 plus 4. That's 10. And 10 equals 4 times 5 over 2, plugging in the formula. So for any value of n, you could check this formula is true. Proving it's true for all n, you know, takes a little more effort unless you use induction. So let's do that. So we'll prove the theorem. Now, whenever you're using a proof by induction, first thing you do is you write down by induction. So we know what you're going to do. And the next thing you need to do is figure out what's your predicate. What's your inductive hypothesis? What's P? All right, so usually P will be the thing you're trying to prove, namely that 1 plus 2 plus 3 up to n is n times n plus 1 over 2. And you state that. You say, let P of n be the proposition, the predicate, that the sum I equals 1 to n of I equals n times n plus 1 over 2. All right, and once you've got that established, now we're going to go verify that P0 is true and that n implies Pn plus 1. All right, so always have to write this down. The next thing to do is to check what's called the base case, P0. So let's do that. All right, so we write down base case. Some people call it the basis step. And we have to check that P0 is true. Well, what's the sum of I equals 1 to 0 of I? 0. There are no terms in this sum. And if I look over there, n times n plus 1 over 2, if n is 0, it equals 0. So we're done with the base case. We've now proved that P0 is true. And the second part is called the inductive step. And here we have to show, for n greater than or equal to 0, we need to show that Pn implies Pn plus 1 is true. Now, how do we show an implication is true? How do I show this is true? What am I going to do to show that's true in general? Yeah? Right, because an implication is true in every case except for true implies false. So if Pn is false, we're done. This implication is true. The only case we have to worry about is P of n is true. So we assume P of n is true, and now we confirm that that means Pn plus 1 is true. All right? So we write that down. Assume Pn is true. And you might also write down for purposes of induction or purposes of verifying the inductive hypothesis, just to let us know why you're assuming it. In other words, you're not assuming Pn is true for purposes of contradiction. You're assuming it for purposes of induction. All right, let's do that. So all right, that means, in this case, i.e., we assume 1 plus 2 plus up to n equals n times n plus 1 over 2. And we need to show that the n plus 1 case is true, namely 1 plus 2 plus n plus 1 equals n plus 1 times n plus 2 over 2. All right? You know, it's sort of weird, and this does confuse people that aren't familiar until you get familiar with induction. It looks like we just assumed what we're trying to prove. We're trying to prove this is true for all n, and we just assumed it. But we're assuming it in the context of establishing this implication is true. And then we apply the induction axiom to conclude Pn is true for all n. All right. Well, let's rewrite this as 1 plus 2 plus n plus 1. Because I've assumed Pn, I can rewrite this as n plus 1 over 2. And now plus n plus 1 out here. That equals, well, I got n squared plus n here over 2 plus 2n plus 2. All right, and that equals n plus 1 times n plus 2 over 2, which is what we're trying to show. So we've completed now the inductive step. We have shown that for all n, Pn implies Pn plus 1, for all n bigger than or equal to 0. Any questions about that? So the proof is done. We've done everything we need to imply induction. We got P0 is true, and Pn implies Pn plus 1 for all n bigger than or equal to 0. Now, induction helped us prove the theorem. Did it help us understand why the theorem is true? Do you have any feel for why the theorem is true after seeing the proof? Not really. No, I don't think, sometimes induction will give you an understanding, sometimes it won't. Here you got no understanding of why the theorem's true, which is sort of unfortunate. Did induction help you figure out the answer to the sum? Namely, say you were trying to derive this answer from this sum. Did induction give you the answer? No. You had to know the answer, namely this, in order to prove it was true. Now, later we'll see examples where induction actually can give you the answer, but often it does not. Often induction gives you no hints, no answer, just proves that it's right once you had the clever idea that, oh, maybe that's the answer. All right, and you'll see that with things like the beaver flu problem. All right, that figuring out the inductive hypothesis or the answer, the details of it is hard, but once you do it, then applying the induction, not so hard, but it gives you a concrete proof. Okay, let's do another one. In fact, we're just going to spend the rest of today doing induction proofs. Okay, so for all natural numbers n, 3 divides n cubed minus n. Means n cubed minus n is a multiple of 3. For example, n is 5. 3 divides 125 minus 5, because it's 120. Let's prove that. And we're going to use induction. What do you suppose Pn is going to be? What's my predicate or my inductive hypothesis here? Any thoughts? Yeah? Yeah, that's you. Go ahead. Yeah. First thing you always want to try is you assume that as your induction hypothesis. So we say let Pn be 3 divides n cubed minus n. What's the next thing we do in our proof? Base case. Always easy to forget, but not a good idea. Base case is n equals 0. And sure enough, 3 divides 0 minus 0. So that's done. What's the next step we do? What is it? Next step? Inductive step. And for that, we're going to need to show for n bigger than or equal to 0, we want to show Pn implies Pn plus 1 is true. So to do that, we assume Pn is true. In other words, we assume that 3 divides n cubed minus n. And we're trying to show that 3 divides n plus 1 cubed minus n plus 1. So we take a look at, we examine n plus 1 cubed minus n plus 1, and we want to show it's a multiple of 3. Well, let's expand that out. This is n cubed plus 3n squared plus 3n plus 1, and I subtract off n plus 1. So I get n cubed plus 3n squared plus 2n. Is this a multiple of 3? I need to show that's a multiple of 3, and then I'd be all done. Is it a multiple of 3? Beats me. It doesn't look like a multiple of 3 necessarily. So maybe we need to massage it a little bit. I do know that this is a multiple of 3. I can use that fact. And in proofs by induction, you always want to, if you're not making use of that fact, then you're not really making use of induction. Sort of a warning sign. So I want to use this fact to prove this. Well, let's get a minus n in here. This equals n cubed minus n plus 3n squared plus, well, if I subtracted an n, I got an add an n plus 3n. So I've rewritten it. Now is it clear? Now it's clear. Very simple, because 3 divides this by Pn, 3 divides that, and 3 divides that. So this is a multiple of 3. All right? Because I've got 3 divides 3n squared, 3 divides 3n, and 3 divides n cubed minus n by Pn, or you could say by the inductive hypothesis. Pn is the inductive hypothesis, another name for it. So therefore, 3 divides that, which means 3 divides this. So that means 3 divides n plus 1 cubed minus n plus 1. And we are done with the proof by induction. Any questions about that one? So the key steps in induction are always the same. You write down proof by induction. You identify your predicate. You do the base case, usually at n equals 0, but it could be something else. And then you do your inductive step. Now, in general, you could start your induction, don't have to start it at 0. You could start it at some value b, some integer b. Let's take a look at that. So you could have, for the base case, you could have p of b is true, not p of 0. And then for your induction step, you would have, for all n bigger than or equal to b, Pn implies Pn plus 1. And then your conclusion is that for all n bigger than or equal to b, Pn is true. So inductions don't always have to start at 0. You can pick where you start. Just make sure that you verify the starting point and you verify the implication for all n at that starting point and beyond. All right, let's now do a false proof using induction. We're going to prove that all horses are the same color. Oops. So let's go through the process. So the proof we write down by induction. Now we need our induction hypothesis, the predicate. So we're going to let that be, we can't let it be this. Why can't this be our predicate? All horses are the same color. What's wrong with making that be the induction hypothesis? You can't plug anything into it. There's no number here. I've got to have a number, an n to induct on. So what I'm going to say is that in any set of n horses, and let's make n bigger than or equal to 1. The horses are all the same color. All right, now if I prove this is true for all n, well, then all horses are the same color. Because in any set of n horses, they're all the same color, so all horses must be the same color. What's the next thing I do? What's the next step? Base case. Now, what am I going to use as my base case here? 1 horse. Okay, or n equals 1. So P of 1. That would say that in any set of 1 horses, the horses are all the same color. Well, that's true. I got 1 horse. It's the same color as itself. So that's easy. It's true since just 1 horse. All right. All right, what's the next step of the proof? What's the next thing I do? Inductive step. So I'm going to assume that Pn is true to prove Pn and show Pn plus 1 is true. All right. So I'm going to assume that in any set of n horses, the horses are all the same color. That I start with. And now I look at a set of n plus 1 horses. So we consider a set of n plus 1 horses. And let's call those horses h1, h2, hn plus 1. What do I know about horses h1 to hn? They're the same color because Pn is true. They're a set of n horses. By P1, they're all the same color. All right. Also, what do I know about h2, h3, and hn plus 1? All the same color because they're a set of n horses. All right. Well, since the color of h1 equals the color of those guys, h2 to hn. I know h1 is the same color as these guys. I also know that hn plus 1 is the same color as those guys. That means that h1 is the same color as hn plus 1, and all n plus 1 are the same color. And that's Pn plus 1. That implies Pn plus 1, and I'm done. Now, a few years ago, we assigned this problem as homework. And we asked students to figure out what went wrong as the problem. Why doesn't this work? And the responses were a little discouraging. Half the class responded effectively as follows. This example just goes to show that induction doesn't always work. A third of the class said, I always knew that you can't trust mathematics. This example just proves it. That really hurt, you know. And most of the rest were something similar to that. Not exactly what we were looking for in the homework. So now we don't leave it to homework. We do it in class. What's the flaw here? What is it? P of n? What's wrong with P of n? No, this is a real assumption. In any set of n horses, depends on n, the horses are all the same color. That is a proposition. Because it depends on n, it's a predicate. It's true or it's false. Now, we know it's false, because you could get a set of a couple of horses with different color. But it is a proposition. Yeah, way back there.
So first we assumed Pn for like a certain set of horses.
Yeah.
So even though it's the same number of horses, so in same number. It was a different set of horses, so it's not something you can assume anymore.
That's a great point. I did gloss over something here because in the predicate I've got in any set. So there's really a for all sets sitting out here. So I got to be careful that I establish that when I'm trying to prove Pn implies Pn plus 1. So to establish Pn plus 1 here, I assume Pn, which means in any set of n horses, they're all the same color. That I'm given. That's Pn. I've got to look at any set of n plus 1 horses. So consider any set, not a set, any set of n plus 1 horses. So you pick any set you want, call them this, h1 through hm plus 1. Well, then the first n are a set of n horses, so I can apply Pn. Therefore, they have the same color. The last n horses in the set are a set of n horses, so I can apply Pn. So these guys all have the same color, and I'm on my merry way here. So you're right, I had to do a little bit more work, but I can do that work, and I still get a proof. Yeah? Good question. There's a problem with the base case. So my base case was here, n equals 1. In any set of one horse, the horses, let's say in the set, just to be really careful, are all the same color. No, in any set of one horses, it's only one horse, so it's the same colors itself. Yeah?
Right.
N plus 1 is not the same as n, yeah?
You can't have the same assumption because it's not a set of n horses, it's a set of n plus 1.
Well, let's see. So you're arguing I made a mistake here, right? Well, I've got horses, horse 2, 3, up to n plus 1. How many horses are in this set here?
Oh, in that set.
In this set, how many horses are there?
N.
N. So I can apply P of n to this set just the same as that set, because P of n is any set of n horses. Well, I'm picking this one now and applying Pn to it. And so therefore, they're all the same color. Yeah?
H1, H2, dot, dot, dot. Like,
Yes.
because it does
That-
work if there's 2 or more, but you didn't prove it was just 1. Or one, from 1 to 2, I guess.
Exactly. Remember I told you that dot, 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 so reasonable, so easy to use, everybody uses it, was going to catch us up? The bug is in the dot, 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 and in particular it has to do with the case n equal 2. So there's 2 ways to look at the bug, dot, 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 or we didn't completely do all the inductive steps. So let's look at the case, actually it's the case n equals 1. Here, in this inductive step, did I prove P1 implies P2? Let's just double check that worked for n equals 1. N equals 1. I've got a set of 2 horses. This becomes 2. So I've got H1, H2. There's nothing in the dot, dot, dot. It's just H1 and H2. Then this becomes H1. So sure enough, H1 is the same color as itself. This becomes, what does this become, this set of horses? What is it really? H2. All right. So I've got the color of H1 equals the color of, oh man, this is so hard to see this bug. I wrote down H2 dot, dot, dot to Hn because take out H1, what's left? What's left is H2 through Hn. But this set is only H1. What's really left here? What is this set? What is this set? H2, H1? No. You see, what is the whole set? H1 dot, 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 Hn. What is the whole thing? It's just H1. Pull out H1 and look at the rest of it. How many horses are here? 0 horses. This is the empty set. There are no horses here to compare to. Even though I got an H2, I got an Hn, I got dot, dot, dot. Because generally, if n's big, this has n minus 1 horses are here. There's n total. I got n minus 1 right here. But n minus 1 is 0. There are no horses here. And so this bridge in the equality totally breaks. All right, I got color of H1 equals, there's no information here, equals the color of H2. There's no equality here. There's no horses in this set. All because of that dot, dot, dot. Do you see where the problem is by using the dot, dot, dot? For the case n equals 1, it was true for every other case of n. N equals 2, n equals 3, it's all true. All right? In fact, what we proved the base case of P1 is true. This is an argument that P2 implies P3. That is true. P3 implies P4. That is true. And so forth. We prove for all n bigger than or equal to 2, Pn implies Pn plus 1. That we proved. What is the one missing implication we did not prove? The missing link, P1 implies P2. We did not prove that. Now, is that true? No. You can find a set of 2 horses that are not the same color, and just because every horse is the same color as itself does not give you that. That was missing in this proof. And so we have to be really careful when you're doing these proofs that you establish the inductive step for all n bigger than or equal to the base case. And then make sure if you're going to use this really convenient dot, dot, dot notation that you don't wind up here saying, oh, this is horses H2 through Hn, when there's no horses there, because n's 1. Any questions about this? Yeah. Great question. All right, let's fix the proof. Start with a base case of P of 2, and now I've got all this done. So therefore, that's another proof. Yeah. Say it again. This is still the same. In any set of n bigger than or equal to 2 horses, all the horses in the set are the same color. That's what he's saying. And he's saying, hey, look, the proof worked here. The inductive step is just fine. P2 does imply P3. Yeah?
Base case P2 isn't true, so...
That's right. The base case fails. All right? That's why you've always got to check the base case. Yeah?
What it does prove is that if you find any 2 horses, and they're always going to be the same color, then all horses have to be the same color.
That is correct. That's a great point. We have given a proof that if you look at any pair of horses and they're the same color, then all horses are the same color. And that's true. That is true. Of course, there are pairs of horses that aren't the same color. So the base case would fail. So always check the base case. You can prove some great stuff if you don't check the base case. All right? All right. Any other questions about that? Yeah. Yeah. Yeah, as long as it's an integer, and as long as you prove Pn implies Pn plus 1 starting there all the way out. Yeah, you can start at negative numbers if you want. Usually there's not many cases where that comes up you want to, but you can. Nothing wrong with that. Any other questions? Yeah, you can see why it was a messy homework problem. All right. So far we've seen examples of how induction is useful in proving the hypothesis is true, but not in solving the problem, per se, or even figuring out what the hypothesis should be. Now, in the last example, we're going to show you how induction can be used to prove there is a solution to a problem, and also how to find the solution. So it's actually going to be a very useful constructive thing in this case. Now, this problem arose in the construction of the Stata Center, the building we're in now. This whole building was originally supposed to cost, completely furnished, under $100 million. That was the goal. But the first mistake they made was the first step was hiring the architect, and they hired Frank Gehry. I think MIT is now in a lawsuit with Frank Gehry. So he was the architect, and costs just went nuts. You know, as you can imagine, all these slanted walls and crazy things happening actually are expensive. And the cost quickly got over $300 million. Literally, that part's true. Now I'm going to fabricate a little bit. Now, actually, fundraising became a huge priority once they're more than $200 million over budget, and they haven't even bought the furniture yet. So some pretty radical ideas were proposed. And one of them was to build a large 2 to the n by 2 to the n courtyard and put a statue of a wealthy potential donor in the center of the courtyard. So let's draw this. So the courtyard, and of course, you know, it's computer science, so it has to be a power of 2. So it's 2 to the n by 2 to the n. And I've drawn here the case n equals 2. And we've got to get the statue of the wealthy guy in the middle. And I'm not supposed to reveal his name, so we're just going to call him Bill. All right, so Bill's got to go in the center. Now, this would be fine, except that nothing was easy with Frank Gehry. Everything is some weird thing going on. And he insisted on using L-shaped tiles for the courtyard. So the tiles that we're going to use look like this. So it's, you know, almost a 2 by 2, except you're missing that piece. So what you need to figure out how to do is tile this courtyard perfectly, leaving one spot for Bill, using tiles like this, these L-shaped tiles. And this is 2 by 2 here. So that's the task. So let's see if we can do that for n equals 2 here. Let's see, we can do a tile here. We can do a tile here, a tile here, a tile here, and a tile there. So we can, in this case, we can tile the courtyard perfectly using these L-shaped tiles, leaving one square in the center for the statue. All right, everybody understand what we're trying to do? The goal? Now I want to do it for n. So let's start proving it by induction, even though we don't know how to do it yet, because we're going to see how induction is going to help us show it's possible and maybe even show us how to do it. All right, so let's state a theorem. For all n, there exists a way to tile a 2 to the n by 2 to the n region, or courtyard, with a center square missing for Bill. And the proof will be by induction. And our induction hypothesis, the predicate, Pn, is going to be what we're trying to prove. All right, so this is the induction hypothesis. Almost always when you do the induction, you want to start out with that as your hypothesis. What's the next step? Base case. Never, ever forget the base case, or you'll be thinking all horses are the same color. P0. Well, the courtyard for n equals 0 is just one square, and that's for Bill. So you're done. There's no tiles at all to worry about. That's easy. So that's true. And then we do the inductive step. Okay, so inductive step. for n bigger than or equal to 0, got to remember to keep track of that now, we assume Pn to verify the inductive hypothesis or to prove Pn plus 1. A lot of ways to write this down, but you always want to say what you're assuming and why. So we need to show Pn plus 1 is true. Well, so let's look at a 2 to the n by 2 to the n plus 1 by 2 to the n plus 1 courtyard. All right, so let's draw it out here. 2 to the n plus 1 by 2 to the n plus 1. What are we going to do to use our inductive hypothesis? Yeah. For them, yeah, so that you're on a good track there for sure. But I got to apply, I'm not going from 1 to 2. I want to use Pn here. So I've got a 2 to the n plus 1 by 2 to the n plus 1 courtyard. How do I use Pn? 2 to the n by 2 to the n courtyard. Yeah?
Oh, never mind. I don't think it works. I was about to say that would be as if 2 to the n would divide that into 4 blocks.
Good idea. Yeah. Let's divide our courtyard into 4 blocks. That's a great idea. And now each of these is 2 to the n by 2 to the n. Right? And I can apply the inductive hypothesis there. Ooh. Yeah. Yeah, it doesn't quite work because Bill wants to be here. Got a little square for Bill there. But I can't use my inductive hypothesis to tile this because there's no square missing. In fact, even if there wasn't a square missing, I'm in trouble. If I've got, say this is size 4 by 4 here. Can I tile a 4 by 4 region with L-shaped tiles? Oh, they're size 3. 3 doesn't divide 16. Yeah.
There's one tile missing from each of those blocks at the corner that intersect. You can fill one tile.
There's a great idea. All right, we're making progress now. Take a corner out of each of them. Put my L-shaped tile here. Now I can use the inductive hypothesis to tile each one of these. Yeah. Yeah.
Well, why can't you put like a 4 in the center, and then you have a bunch of 2s on the side?
4 in the center and a bunch.
Like a 2 by 2 in the center.
I got that. I got Bill and a tile.
And then, but like, make it bigger. Not just like 4 single tiles, but like, you have something like that over there, right? Put that in the center.
Put that in the center. Okay.
The rest of them will have like 2 by 2, which you know are sort of basics.
Well, the rest of them aren't 2 by 2 because this is n. I got to use Pn here. And Pn says that I can, in a region 2 to the n by 2 to the n with a square out of the center, I can tile it. Did I make it? Am I good here so far? I claimed I was sort of done. Yeah. What?
No, because P of n tells us, well, assuming P of n tells us that we can set up a 2 to the n by 2 to the n courtyard with a centerpiece.
Yeah.
Has like a spot for Bill.
Yeah. And what's the problem for this 2 to the n by 2 to the n region? Bill's not in the center. He wants to be in the center. We put Bill in the corner. So you can't use the inductive hypothesis here. So I went a little too fast here. This is not a proof so far. I got a problem. Yeah? Great. OK, let's then change the inductive hypothesis. Good. Let's say there exists a way to tile a 2 to the n by 2 to the n region with a corner square missing. For Bill. All right. Oh. But then I got to put, Oh, but I can make this work. Yeah, we can make something. We can prove this now. The inductive step's going to work because I'll put Bill, say he's in one of the 4 regions, then use the L down here, put the L here, and now I've got a corner out of each one, and now I'm done by induction. I have proved there's a way to tile any 2 to the n by 2 to the n region with a corner square missing. I think that proof works, yeah?
With Bill in the middle, because when you prove that you can put Bill in the corner in a 2 by 2 case, you can just blow that square up, and that square where Bill was becomes just another square, which is 4 by 4, and then you can put them in the middle.
That is true. So you've jumped ahead. We have successfully now proved this is true for P of n. But Bill didn't want to be in the corner. We're trying to prove there's a way to do it with Bill in the center, which is not what we proved. And you come up with a way, yeah, that might be doable. First prove you can put Bill in the corner and do it in 2 to the n by 2 to the n's. Oh, I don't know about this, actually. I got Bill in the corner. There's some way to do it, but it might have involved doing this, and now I can't rotate that. I don't think that proof necessarily works.
He could be here, but likewise, we could prove that if the block just rotates, you can be in the
Yes, I agree with you, and I liked it when I first heard it, and you might still convince me, but all we proved is this. There's a 2 to the n by 2 to the n, any 2 to the n by 2 to the n region, we can tile it with a corner, Bill in a corner, any corner square missing.
Yeah, any corner square.
Good. So now you want to say, I can get Bill in the middle. And what you want to say is, OK, I tile this region with Bill here in a 2 to the n by... maybe you're right. So then I would apply the theorem here with Bill here. Oh, Bill here. No, I think I like it now. There, and then I would take these out.
The L squares are going to fit because each L square just takes up 3 blocks. And that big square is just like a zoomed out version of like the little square.
I like that.
Since you know that little square fits in like a 2 by 2, like for example in the 4 by 4 case, we proved the 2 by 2 case. In the 4 by 4 case, you have like a big size. It's just like you have 4 squares, right? And each of those 4 squares has 4 squares. So you take that top right square, and you put Bill within the smaller square, where exactly where you want them to be, and then you fill those others, like all those empty spaces with.
I agree. You can make a proof, and so in this case, you'd make a lemma that uses induction that says you can do it with Bill in the corner, and then as a corollary or a theorem, you'd take that and apply it to 4 subsquares, put Bill in here, take these out, and then now you have your result with Bill in the center. So that is a way to do it. It ends up being more complicated. There is a simpler approach, but that is a way that works, and is a natural thing you would do if you had this on homework. Is you'd think of a different thing to prove by induction, then use that as a lemma to get you where you wanted to go. There's another way to do it without having that first step. All right, and that's,
For example, on that courtyard where n equals 2, divide each cell into a 2 by 2. Something.
Well, yeah.
Anyway,
You want to do it bottoms up. You want to take it and divide it, and make that your inductive step by 2 by 2s inside. I haven't thought about that approach.
So then you can tile that L-shaped tile with 4 smaller L-shaped tiles. So if you can do that, then you're all set except for the 2 by 2 where Bill originally was.
I'm worried about a lot of 2 by 2s with a corner missing if I do it that way. I have to think about that. Let me get to another approach here. we couldn't make it work with the center. We could make it work with the corner, but then we had to do more work after. One general technique to use with induction, when you're struggling, what's the induction hypothesis to use? If what you got doesn't work, you could pick a different one, but better to pick a stronger one. Yeah? Yes, you could, and that is a good thing to do. Make the induction hypothesis be much stronger. I had trouble proving there's a way to do it with the center square missing. Turns out to be easier to prove it where you assume any square could be missing. Seems like this should be harder, right? We had a hard enough time just showing this square missing was doable. But by assuming something, by trying to prove a harder problem, assuming something stronger in Pn, it gets easier to prove. All right, now we better check the base case, P0, but that's easy. There's only one square Bill can be. All right, but now let's look at Pn implies Pn plus 1. All right, so we go back to this. We've got a 2 to the n plus 1 by 2 to the n plus 1 courtyard. And now Bill can be anywhere. Put him here. There's Bill. Now I'm going to place my first L-shaped tile here in the other three regions. And now I apply Pn to each region. Well, Pn says I can do it with any square missing. So I'll pick this one out here, this one out here, that one there, and that one there. And now I'm done. And that was easy. No extra steps. Now, how is it possible that it was easier to prove something that was harder? Yeah?
By forcing it to be in the center of the corner, you're putting another constraint on yourself.
Yes, that is true, but by allowing him to be anywhere, I could have started, that's a possibility. See, what I'm trying to do here, this inductive step is all about proving Pn implies Pn plus 1 is true. That's what I'm trying to show. Now, how is it useful for me if Pn is stronger, has more?
Well, when you say any, and you grow it, you prove that it can be in, say, the corner. Well, but when you grow it, the corner moves. But since we proved that it can be in any, it's fine if it moves.
Exactly. That's exactly right. Pn got more powerful, which means I get more to assume here. In the recursive problem, Bill can be anywhere now. It gives me more power. I can tile any courtyard with a courtyard with any square missing. This is more powerful. So this got more powerful. So did this. So what it means is my tool set is bigger with a stronger Pn. And what I'm trying to construct or prove got harder. And sometimes, if I've got more tools, it becomes easier to prove even a harder thing. And so a general rule with induction is if you don't first succeed, try again. Well, the rule with induction is if you don't succeed at first, try something harder. All right? And it's amazing, but it actually works a lot of the time, as it did here. If I don't assume something strong enough, and Pn is some little weak thing like Bill just in the center, it's not enough to go anywhere. But if I can assume a lot more, like Bill can be anywhere he pleases, then I can prove lots of things here. All right, so you see, so it's all the art, and you're going to learn this over the next several weeks. It's all the art of what's your induction hypothesis. Picking a good one, life is easy. Picking the wrong one, very painful, as you'll see with beaver flu. Okay, that's it for today.
Throw your stuff away. Don't hesitate. Don't be scared. New ways will appear in front of you. New wealth too. I know it's a bad day, catching every teardrop. Try to tame a hurricane. day by day. Day by day. Day by day. Day by day. Big feelings coming closer. It's okay. You're taught the opposite. Let's rewire. I know it's a bad day, catching every teardrop. Try to tame a hurricane. Wish you didn't feel alive. But if you try to embrace rather than push away, you will find this place getting better day by day. Oh, listen to the words I say. You can take it day by day. Listen to the words I say. I know it's a bad day, catching every teardrop. Try to tame a hurricane. Wish you didn't feel alive. But if you try to embrace rather than push away, you will find this place getting better day by day. Day by day. Day by day. Day by day. Simple, simple, simple minds. I guess we'll take it one by one, baby, one by one. Just different, different, different kinds. We'll try to take it one by one, baby, one by one. Too many problems, I'm already lost, yeah. My baby, I do. I miss you too many nights. I miss your colorful lights. I think I love you too much. I miss your blueberry eyes. Fine, fine. I play the memories over, over, over. Just tell me in my mind. I'm trying to keep it in sober, sober, sober. Oh, simple, simple, simple minds. I guess we'll take it one by one, baby, one by one. Just different, different, different kinds. We'll try to take it one by one, baby, one by one. I keep stepping off all times I'm laughing over. I keep wanting you too long. I keep tripping on myself, thinking you're my lover. I've been way too long. Honestly, baby, I can't tell you why we can't be standing by each other's side. I wanna know my true feelings inside. Give me some time. Oh, we'll bring it in a simple, simple, simple minds. I guess we'll take it one by one, baby, one by one. Just different, different, different kinds. We'll try to take it one by one, baby, one by one. Simple, simple, simple minds. I guess we'll take it one by one, baby, one by one. Just different, different, different kinds. We'll try to take it one by one, baby, one by one.
The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseWare continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseWare at ocw.mit.edu.
Now, generally speaking, a proof is going to have 7 characteristics that you want to keep in mind. Good proofs are correct. That's obviously important. Complete. You got to have all the details there. All the key steps have to be there. They should be clear so we can understand what's going on. Brief is good. You know, you don't want to crush somebody with all the details. You want to get to the key points and be crisp. It's really nice if they're elegant. Now, that means clever. It's the mathematician's notion of beauty. Like you go to the art museum and the artist will say, wow, that's a beautiful painting. In mathematics, you say, wow, that's an elegant proof. It's crisp, clever, short, to the point, and it's really the highest compliment you can get. Now, from a mathematician anyway. And there's a lot of judgment that goes into that. Just like in art, there's judgment over what is great art. The proof should be well organized. You know, for example, use lemmas the same way you would use subroutines in writing code. Helps to make it clear. And the proof should be in order. You know, sometimes you'll see proofs where things are done in a haphazard fashion. All the pieces are there, but they're in the wrong order. Sometimes, and they teach this in some high schools, they teach you to do proofs backwards. You know, and the classic thing there is, say you're trying to prove A equals B. Well, the proof sometimes they'll start with what you're trying to prove, and then they'll do a bunch of steps, and then you'll end up with 1 equals 1, and you'll write a check. Because you went from A equals B to 1 equals 1. And that's, of course, true. Now, that's not a good thing to do. It can be correct if the implications go this way. Because really, you're starting with a fact, 1 equals 1, and deriving A equals B. So if, in fact, the implications work this way, then your proof is right. But most people, especially as you get farther along, think about it going from top to bottom. Okay, so don't use this technique, because it'll confuse people. You're liable to make a mistake. Just start with 1 equals 1 and work your way from there, top down, for being in order. Now, good proofs are very much like good code. You know, in fact, one of the reasons we care so much about teaching you how to write a good proof in computer science is so that later on, you'll be able to prove that your programs are doing what you expect, what they're supposed to do. Now, there are many famous examples where programs did not do what they were supposed to do with disastrous consequences. You know, the Airbus A300 was one of the first commercial jets totally operated by software. Could take off, fly, and land totally by software. It was a major advance, you know, in the airline industry. The only problem was that on one of the first flights of the A300, the software accidentally opened the rear door just before landing, and the plane crashed as a result. It's the first plane crash in commercial history because of a software bug. There's a famous radiation device for cancer patients called the Therac 25. It's famous because it got into a race condition occasionally, which caused the device to just slam the patient with radiation, so much so, killed the patient. And they had multiple examples of this. Of course, a lot of lawsuits afterwards. How many of you all remember the 2000 election? A few of you do. Okay. This will probably be the last class that remembers that. But that's where, you know, Al Gore was going up against George Bush. Very close election. All came down to recounting the votes in Florida. But in fact, Al Gore got negative 16,000 votes in one county because of a software bug in the electronic voting booths, which I think they got rid of a lot of them in the election after that because the software was buggy. So poor Al had enough problem with Chads and funny business in Florida, but getting negative 16,000 votes certainly didn't help his chances. Several years ago, a single faulty command in a computer system used by United and American Airlines grounded the entire fleets of both airlines for close to a day because they couldn't do anything. They're all run by computer, and the whole thing was screwed up. So there's lots more examples. We run into this issue all the time at Akamai. Akamai is a company started by MIT folks, by myself and Danny Lewin and a dozen undergrads in the late 1990s. And we deliver a lot of the content you get on the web, Facebook, all the search engines. A lot of the stuff you go to comes from our servers. So we got to be very careful that we don't have software bugs. Now, in fact, we do, and we catch them every once in a while. But if we got a bad one, it would bring down all the sites you go to. You wouldn't be able to go to those sites anymore. And everybody would notice. It would be sort of embarrassing. Now, this really does matter. And this is going to sound a little scary, but someday, probably 30, 20 years from now, somewhere in there, it's possible that all of us, our lives may depend on the software that some of you write. In fact, to bring this home, how scary it is, look at the person sitting next to you. And imagine that in 25 years, your life depends on whether their code does what it's supposed to do. A little scary, That's why we are very motivated to help you learn how to make rock-solid arguments. All right? So you don't have code that fries one of your classmates someday or puts him in a bad plane situation. Now, unfortunately, writing rock-solid proofs is a very hard thing to do. Even the world's best mathematicians mess them up on a regular basis. In fact, it's estimated that 1/3 of all published proofs have bugs, have flaws that render the proof incorrect. The trouble often arises because we get lazy. We don't write down all the details or all the steps because, wow, it's clear. Let's just move on. Now, this can be okay. Not such a good practice, but it dramatically increases the chances of making a mistake. And there's some very famous examples in the math literature from the world's most famous mathematicians. Gauss, and we'll talk about Gauss later during the term. He's one of the most famous mathematicians ever. He wrote his PhD thesis in 1799. And it's usually referred to as the first rigorous proof of the fundamental theorem of algebra. And that says that every polynomial has a 0 over the complex numbers, something probably a lot of you learned in high school. You get a polynomial, you can find roots of the polynomial over the complex numbers. But his thesis contains the following quote: "If a branch of an algebraic curve enters a bounded region, it must necessarily leave again. Nobody, to my knowledge, has ever doubted this fact." Warning signs, buzzers should be going off in your brain. "But if anybody desires it, then on another occasion I intend to give a demonstration which will leave no doubt." So he's using something that he believes to be true. He sort of thinks it's clear, that everybody knows it, but he writes this down. And when you're writing that down, you know there's a problem. And in fact, there's another Fields medalist. We talked about Fields medals last week. Stephen Smale writes that this was an immense gap in the proof that was not filled until 1920, more than 100 years later. So Gauss never could give the proof, and nobody did for over a century more. Remember the Poincaré conjecture from last week? We had Colbert talking about that. In 1900, Poincaré claimed it was a simple fact. 4 years later, he decided it wasn't so simple, and he demoted his claim to the status of a conjecture. And of course, this became the famous Poincaré conjecture, which took another century to solve. All right, so when you think you see yourself doing this, famous mathematicians do it too, and it catches them. So you want to not try to do that. Now, in fact, just to really bring home the point, we've made a top 10 list of proof techniques you should not use in 604.2. So everybody go to the handout here. In fact, there's a lot of them on the back too, but on the front page there's the top 10. So we're going to go through these. These are the ones we've most observed in 604.2 over the years. Number 10, proof by throwing in the kitchen sink. The author writes down every theorem known to mankind and then adds a few more for good measure. Now this is good because when you're questioned later, you're trying to get a better score on your exam, You say, look, the proof contains all the key facts. They're all here. And so that does help. You get extra credit if all the facts are there. We have literally seen students copy over their crib sheet if they got enough time for a problem they're not knowing how to solve, just to get all the facts in there. Number 9, proof by example. The author gives the case n equals 2 and suggests it contains most of the ideas of the general proof. In fact, a student before class was telling me on one of the homework problems, he talked about it to his non-math friends, and they gave examples, not the proof. Number 8, proof by vigorous hand waving. One of my favorites, I get up here and wave my hands, and it must be true. Okay, number 7, proof by cumbersome notation. Here the reader gets hopelessly confused, gives up, and says, okay. In fact, I once had a grad student, and we called him the encryptor, because he could take the simplest proof and so encrypt it in notation and God knows what, you could never understand the proof. And you figure out if it was really right or wrong. That goes well with number 6, proof by exhaustion. So does throwing in the kitchen sink. Number 5, proof by omission. You will see that a lot, also by faculty. The reader may easily supply the details. The other cases are analogous. Trivial. Experts use that all the time. You can find a lot of my papers online. The proof is trivial. Very bad. Every once in a while, it turned out not to be so trivial. Number 4, proof by picture. We've seen those. Saw one on Tuesday. Number 3, proof by vehement assertion, sort of like the hand waving. The more forceful you are in your argument, the higher you raise your voice, the more intimidating you become. Doesn't make it more true. Number 2, proof by appeal to intuition. Now you say, any moron knows that. Well, you're sort of reluctant to now question it. And then number 1, proof by reference to eminent authority. I saw Fermat in the elevator and he said he had a proof. I don't think so. Fermat's been dead for over 300 years, and he was not so reliable in the first place. In fact, he has one of the most famous assertions that turned into a conjecture called Fermat's last theorem. And it was not really a theorem by the time he died. How many people have heard of Fermat's last theorem? Raise your hand. Yeah, pretty famous. It's the one theorem he proved that actually he didn't prove. It says for all n bigger than 2, there does not exist an x, y, and z in the natural numbers plus the positive natural numbers such that x to the n plus y to the n equals z to the n. Now, of course, for n equals 2, that's just the Pythagorean theorem. You can find like 3, 4, and 5 when you square them, satisfy that. But it says this does not work for any higher value, any higher power than 2. Now, in 1637, Fermat wrote in the margin of a book that he had discovered a proof of this result, but the proof was too long to fit in the margin. And so he wasn't going to supply the details there. And he never did supply the details, and it took 350 years and hundreds of pages. A fellow named Andrew Wiles, took him personally over 10 years. He more or less locked himself in his room for 10 years, produced hundreds of pages, and he finally did prove Fermat's last theorem. Fermat was right about one thing. It would not fit in the margin. At least there's no proof that we know of that would fit in the margin of a book. Any questions on proof technique? We're going to pound a lot on this over the next few weeks. All right, next we're going to look at a class of puzzles that was very popular in the late 1800s. Now, in these puzzles, you have a grid of letters or numbers, and you got to slide the letters and numbers around to put them in order. And so as an example, here's the problem on a 3x3 grid or an 8 puzzle. You want to find a sequence of moves to go from this configuration. I'll do a 3x3 case. I got A here, B here, C, D, E, F. And I've put G and H out of order. and that square is blank, and I can move tiles or letters into it. I want to start here, and I eventually want to get to the configuration where the letters are all in alphabetical order. So G and H are in order. Now, a legal move means you slide a letter into an adjacent blank square. And you can go in a row or a column. Okay, everybody understand the game? What you're supposed to do? You slide these things, that could go down, that could go across. How many people played the game like this before? Good, good, good. A lot of you. Okay, so I need some volunteers who are good at solving puzzles that can do this, have played games like this, that are pretty quick at it. All right. So I've got it here. All right, who'd like to come down? There's prizes if you can solve this. What we're going to do is solve this and see if you can solve it in 3 minutes. But I need 3 students to come on down and do this. Who'd like to volunteer? Who thinks they can handle puzzles under pressure? So you got the G and H out of order. See, it's not so hard. You move the F down there. I don't know. Play around like that. So I need some volunteers. Who'd like to come down and do this? You can win candy. I got candy here. There's even a prize if you don't make it in 3 minutes. Who wants some candy? Nobody? What's that? There is. Come on down. All right. Now, who's going to help him out? I need a couple more people here just to mess him up, because by himself, there we go. Good. Anybody else like to come on down? Because if we get 3, it really gets hard, because you fight over what moves to make. Now, what I'd like you all to do is sort of scream out possibilities for him. Like you figured out there, if you scream out, that'll really screw him up. Okay, so now you can't pick him up. You just got to slide him around. And you can go, and we'll go to 256 and see if you can solve it. If you can solve it, you guys get candy. And if you can figure it out there, let them know. No, you can't use the gray area. All right, you got about 2 minutes. Oh, they got the G and H in order. Everything else is pretty well screwed up, though. What do you got? A, B, C, D, E, F, H, G. No, that's where you started, guys. That's not it. It was close, yeah. Just one was out of order is all, but just one letter at a time. There you go. I think they need help. You got about a minute to go.
Cannot see anything.
You can't see anything. Well, I don't know if it would help. You want to show them where you are? This is not looking good. Yeah, we're pretty close to the end here, guys. ABC, FED, GH. GH is good. F is not so good. All right, you got about 30 seconds. Whoa. What are you guys doing? One at a time here. One at a time. In fact, I think time is up here. All right. All right, 256. Oh, no. That we don't do. No diagonal moves. No. All right, well, now you guys are good sports, so you do get a prize. It's not the candy. but I have these wonderful plastic Nerd Pride pocket protectors for you. There you go. Very good sports. Thank you. Well done. All right. Now, I was a little cruel to these guys. Can anybody, for a lot of reasons. It's impossible? You think? Yeah, it is impossible. This is impossible to do. Let's see if we can prove it's impossible. Because it doesn't seem so hard necessarily. But let's take that as a theorem. There is no sequence of legal moves. You know, diagonal moves makes this a lot easier. To invert G and H and also return all the other letters to their original order or position. Now, to prove this, we're going to use what's called an invariant. It's a very powerful and commonly used concept in computer science, very closely tied to induction, as we'll see. In order to show that your system can never reach a particular special state, it is sufficient to show there's some property called the invariant that holds at the initial state and that is preserved by every legal move and is not present, does not hold in that special state. The idea is if you get this magic property called the invariant and it holds at the start and it holds across every step, then the only states you can reach have to have the property, the invariant. And if the special state doesn't have that property, you can't reach it. All right? So there is going to be some property we're going to look for that held at the beginning here. In the beginning had this setup. That holds, it's preserved by every move, every legal move, but does not hold in this state. And therefore, you could never reach this state legally. So they were doomed. So we got to figure out what that property is. And that's always the trick in analyzing systems or algorithms is what's that key property, the invariant property. So to figure out the invariant, we sort of have to look at what happens during a move in this system, a transition. Well, there's two kinds of moves. There's a row move. And an example of a row move is you might have A, B, C, D, G, E, F, H. And I'm going to move the G in its row to the blank square. So it would become this state. So G moves rightward into the blank, and the rest stays the same. Now, when I make a row move, did the relative order of the items change? No. In fact, of course, to be precise, I better define what relative order means, or the natural order. So by the natural order, I mean this ordering. 1, 2, 3, 4, 5, 6, 7, 8, 9. So if I look at the order here, G moved from 5 to 6, but didn't change its order with respect to any of the other guys. All right, let's state that as a lemma. Because that'll be very useful. Lemma 1. A row move does not change the order of the items, of the letters. Proof, well, it's obvious. No, you can't let me get away with that, right? Because I'm not going to let you get away with that on homework. That's not so good. So we've got to be a little more careful in the proof here. Otherwise, we'll just head down the path to trouble. So let's sort of specify, what does a row move mean? Just get some little bit of math and specification around it. Well, in a row move, we move an item, a letter, from some cell I, whatever I could be anything, 1 to 9, into an adjacent cell What are the possibilities for the adjacent cell? Plus or minus 1, yeah. Okay, into cell I minus 1 or I plus 1. Nothing else moves. Hence, the order of the items is preserved. Because if you're going with I to I plus 1, everything else is in I minus 1 or less, I plus 2 or more. Relative order does not change in this case. All right, and I'll claim that's enough. All right, you know that I've thought about it a little bit. I've really quantified that I goes to I minus 1 or I plus 1. Nothing else moves. Therefore, we're done. Now, I could have added some more sentences here like I talked about, but this is probably enough in this case for this guy. So let's then look at in fact, if we only had row moves, there's not much that happens. The order never changes with row moves. So we never get there, but column moves are more interesting. So as an example of a column move, we have A, B, C, D, F, H, E, G. Say I move the G up. Then I would get this one. A, B, C, D, F, G, because G moved up, H, E. So G went to there. Did the ordering change for this move? Yeah. How so? What things changed order? Which pairs of letters changed order? G changed by 3, moved 3 in the order. And what letters did it change relative order with? Yeah, the 2 preceding it. G used to be after H and E. Now it's before H and E. All right, so it changed relative order with 2 items. It changed its position by 3, moved up 3 in the ordering. And so it changed order with the 2 in between. Let's look at another one. Because we're really doing these examples to hunt for an invariant is what we're trying to do here. Something that will let us prove we can never get to the desired state. All right, let's look at this one. A, B, C, D, G, H, E, F goes to, I'm going to move B down this time. A, C, D, B, G, H, E, F. So B moves down. The relative order changes. Which pairs got changed in their relative order? B changed with C and E. C and D. B used to be before C and D. When it moves down here, it goes after C and D. Any guess about what lemma 2 is going to be? What happens when we make a column move? Change the order of good. So a column move changes the order of a guy with the previous two or the next two, which means the relative order of two pairs change. So let's take that as lemma 2. Yeah, when we say don't do proof by example, we don't mean don't try examples. Because by trying examples, you find out what you're trying to prove. Right? So that's good to do. A column move changes the relative order of precisely two pairs of items. So let's prove that. In a column move, we move an item in cell I, for some I, to a blank spot in cell what? I minus 3 or I plus 3? Okay. And just to see that, let's draw out the natural order. I got 1, 2, 3, 4, 5, 6, 7, 8, 9. Column moves could be here, 1 to 4 and 4 to 1, 2 and 5, 3 and 6, 4 and 7, 5 and 8, 6 and 9. All 12 possible column moves this works for. They're always separated by 3. And when an item moves 3 positions, it changes relative order with 2 other items. And you can even write down what they are. It's I minus 1, I minus 2, or I plus 1, I plus 2. Those are the guys it changes order with. All right, we got 2 lemmas here. That one's done now. In a row move, order does not change. In a column move, 2 pairs of letters get flipped. That's all you can do with this puzzle now. So can anybody think of something we can work with to get an invariant here? Something that won't change? What we should be focusing on? Yeah?
You can only move 2 pairs. You can only switch 2 pairs of items at a time. So if there's not, so if you don't have an even number of things at a place, you can't switch from one thing to another.
Yeah, that's good. So really to focus in on there is if you have an even number of things out of order to start, you're going to have an even number forever because you can only change 2 at a time. That's a great idea. Let's really specify that now and define that. A pair of letters or items, call them L1 and L2, they form an inversion, or called an inverted pair. Also known as an inverted pair. If L1 precedes L2 in the alphabet, but L1 appears after L2 in the puzzle. All right, so that is an inversion. So for example, let's see, how many inversions do we have in this case? Got A, B, C, F, D, G, E, H. How many inversions are there in that state of the puzzle? Yeah? Three, good. And what are they?
D is after F.
Yeah, DF is an inversion. EF is an inversion. And what's the last one? EG is an inversion. Yes, so the answer is there's 3 inversions in this puzzle. And if I keep doing row and column moves to this, what do I know about the parity of the number of inversions? Will always be odd. That's sort of interesting. Okay. Now, how many inverted pairs are there in the start state, way back over here? How many inverted pairs here? 1 inversion. How many inversions here? 0. All right. And can you see where we're going to head here now? If I started with 1, that's odd. And every time I do a row move or column move, it's going to stay odd. And I can never get here. Is that clear, what we're trying to do? So let's keep doing it. All right, let's go over here. All right, so now we'll use lemma 1 and lemma 2 to create this notion that we only change the number of inversions by an even number in lemma 3. During a move, the number of inversions can only increase by 2, decrease by 2, or stay the same. All right, and this proof is pretty easy. There's a couple of cases. In a row move, what happens? How does the number of inversions change in a row move? Stays the same. No changes. And that's by lemma 1. Now in a column move, there's 3 cases. Well, we know 2 pairs change order. That we know. That's lemma 2. All right, by lemma 2 we know that. But the 3 cases are, let me start on the next board. So case A is that both of the inverted pairs were in order originally, before the column move. What happens to the number of inversions in this case as a result of the column move? Goes up by 2. Case B is that both pairs were inverted before I made the column move. What happens to the number of inversions in that case? Decreases by 2. They were in order, so they were inverted. Now, when I flop them, they become in order. So inversions drops by 2. And case C is there's one of each. One of the pairs was inverted. The other wasn't. What happens to the number of inversions in that case? Yeah, stays the same. All right, and we're done. That's what the lemma says. It can go up by 2, down by 2, or stay the same. All right, now a simple corollary of this is that during a move, the parity, i.e. even or odd, of the number of inversions stays the same. It can't change at all. During a move, the parity, and the parity means even, odd. Sometimes it's called 0, 1. But the evenness or the oddness of the number of inversions does not change. Where? Oops. I mean one pair is inverted, one pair is not. No, I mean two pairs change order in a column move. Right? Let's go back and look at that. So I'm doing a column move. For example, G goes up, GH changes order, GE changes order. G changes order with these two guys, so there's two pairs that got flipped. All right? So in a column move, two pairs reverse their order. If they were in order, they become inverted. If they were inverted, they become in order. Any other questions? Yeah?
So we're saying that letters can be members of like more than one pair?
Yes, a letter can be in, the letter E is in 7 pairs, because there's 7 other letters. And in fact, we're looking at a space of, what, 8 times 7 divided by 2, 28 pairs of letters. So there could be 28 inversions if they're all out of order. Any other questions? Okay. Well, we're getting there. We're almost done. I got to prove this corollary that during a move, the evenness or oddness of the number of inversions does not change. And that's because adding or subtracting 2 from a number does not change its parity. Stays odd or stays even. So adding or subtracting 2 does not change the parity. All right, now we're ready to state the invariant. Anybody tell me what the invariant is going to be? What's the invariant going to be in this system? Yeah, the parity of the number of inversions is odd. Because it starts that way, it's preserved, and it won't hold in the desired end state that we're looking at. So we can state that as follows. In every state or configuration reachable from the start state, which is A, B, C, D, E, F, H, G, which are out of order, the parity of the number of inversions is odd. All right, and the proof will be by induction. And invariant proofs are always by induction. And the inductive hypothesis, and this is very typical in a proof by using invariance, is so P of n is after any sequence of n moves from the start state. Well, in fact, just the rest of this is what it is. All right, so our inductive hypothesis is P of n after any sequence of n moves. So n is the number of moves you took to get there. From the start state, the parity of the number of inversions is odd. That is the inductive hypothesis. This is the invariant, and they become one and the same. And the parameter n is the number of moves you've taken. And that's how you set up a proof using an invariant. It always looks just like this. OK, so we're doing a proof by induction. We've got the inductive hypothesis. What's the next step? Base case. And in these circumstances with a proof by invariant, the base case is always 0. We haven't made any moves yet. Now in this case, if we haven't made moves, the number of inversions is the start in the start state now is 1. That means the parity is odd, and the hypothesis is satisfied. P of 0 is true, because in any sequence of 0 moves after this, i.e. in this state, you got 1 inversion that's odd. Last step is the inductive step. And here we need to show for any n bigger than or equal to 0, we need to show P of n implies P of n plus 1 is true. All right, the standard thing. So let's look at Pn plus 1. That's talking about where we are after a sequence of n plus 1 moves in the puzzle, in the start state. So let's consider any sequence of n plus 1 moves. And call these moves, label them by m1 all the way to mn plus 1. Those are the moves we made. Now, by the inductive hypothesis, because of Pn, we know that after the first n moves, the parity is still odd. That's what Pn says. All right, that's Pn. After any sequence of n moves from here, the parity of the number of inversions is odd. So we could say by the inductive hypothesis, or we could say by Pn, we know that the parity after moves m1 out to mn is odd. Now, by corollary 1, do we still have corollary 1? Lemma 4. Corollary, yeah, good. We got corollary 1. During any move, the parity doesn't change. That says from the nth, after the nth move to after the n plus first move, one extra move doesn't change the parity. So it's still odd. right, so next, by corollary 1, we know that the parity, the number of inversions, does not change during mn plus 1. Therefore, this implies that the parity after all n plus 1 moves, these guys, is odd. Started odd, it stayed odd after the first n, it stayed odd during the n plus first, so it's odd. And that's exactly the statement of Pn plus 1. So we've completed the induction. We've shown that Pn implies Pn plus 1. All right, so now we've, any questions so far on this? Yeah?
What's the difference between a lemma and a corollary?
You know, really, there's not a lot of difference. Corollary usually is something that's a simple consequence of something else. And the corollary was at a pretty short proof. Usually when you see corollary, there's not a 10-page proof there. Lemma is something that you're going to use as a tool for a bigger thing, often a theorem or another lemma. In fact, now we're going to get to the theorem, which is sort of the final thing, the thing we're really after. And that's sort of the big deal. And now the proof will be simple because we've done all these lemmas and corollaries. Any other questions? All right. In fact, did I write? Oh, the theorem. Yeah, the theorem's up here, right? There is no sequence of legal moves to invert G and H. In other words, the students were screwed. They couldn't do it fairly. So let's prove the theorem now. The parity of the number of inversions in the desired state, i.e. in order, the target state, is even. Nothing's out of order. There's 0 inversions. By lemma 4, the desired state cannot be reached from the start state because its parity is odd. Using legal moves. So we're done. So the proof of the theorem by now is short, because we did 4 lemmas, a corollary, and lots of argument. Could you have solved the puzzle if I allow the blank to be somewhere else at the end? Is the puzzle solvable then? No. Why not? Doesn't impact the parity at all, so you can't do that. Okay. Again, the idea here, and you'll get some practice and homework, is you're looking for a property that holds the beginning, is preserved by every step, but is not present in the target state. All right. Now, actually, this puzzle was enormously popular in the late 1880s. In fact, there was a $1,000 prize offered for anybody who could solve the larger version. Back then, it was the 15 puzzle, which you can still buy today. Same problem on a 4x4 grid. Exactly the same problem. A pair is out of order. You got to get them in order. You can't do it. Now, the proof you can't do it is a little harder. Same idea, one extra idea in it, one extra lemma, and that's for homework. All right, so you'll go through and see exactly the structure with one extra little trick in it. But back then, I guess most people didn't, well, of course, most people didn't realize it wasn't doable, so they could offer this prize safely. You know, $1,000 then, probably worth $250,000 today. Any questions on the 8 puzzle? Or yeah?
The inductive steps, when you said by inductive hypothesis, and that parity after, shouldn't the first term be M0?
Let's see. No, the moves are, we have the first move is M1, the second is M2. Now, when I talk about 0 moves, that means no moves have taken place. I'm still in the start state. So a move is a transition between states. So you could have state 0. That's the start state. State 1 would be the move, state after move 1. Have I got that right here? So the inductive step, I'm showing that, yeah, P0, I need to show P0 implies P1, P1 implies P2, and so forth. And Pn is the parity of inversions after n moves. So you could have state S0. We didn't label the states here, but you could have state S0. Yeah?
So in this problem, we assume that everything should be defined as a row move or a column move.
Yeah.
How do we know when those types of assumptions are valid?
Well, that's a good question. OK, so really there's 2 cases. We'd have to sort of, to be really precise, we should have argued there's only 2 types of moves, a row move and a column move. And in fact, if you look at what can move into a blank square, there's 4 guys that can do it. The guy above, the guy to the right, the guy to the left, and the guy below. 2 of those are row moves, 2 are column moves. So that's right. To really pin down the details, we should have checked those are the only 2 possible moves. And if there was a third kind of move that I hadn't considered, this proof would be bogus. That's a good question. Any other questions? OK. Now, I think probably you see why the invariants are important. But you know, say that someday you're building software to run a nuclear reactor. Now, there's a certain state you'd really like to avoid, meltdown. And you'd like to be able to prove that in any sequence of moves that happen in your reactor program, you never reach the meltdown state. Well, you'd use invariants to do that. Or if you're building software for an airplane, you'd like to never reach the crash state. Or if you're building a radiation device, you never want to get in a state that fries the patient. So these things actually, this is an important notion. All right, for the rest of the day, we're going to talk about a different kind of induction called strong induction. It's very similar to ordinary induction, but it's a little easier to use when solving certain problems. Now, like regular induction, strong induction can be expressed with an axiom. So let me show you the strong induction axiom. You have a predicate, Pn, like before. If P0 is true, your base case, and for all n, it's not Pn implies Pn plus 1. It's P0 and P1 and and Pn are all true, then Pn plus 1. OK, if this is true for all n, then Pn is true for all n. All right, now the only difference between strong induction and ordinary induction that we did last time is this part. In ordinary induction, you're showing that Pn implies Pn plus 1. In strong induction, you're showing that all these facts put together imply Pn plus 1. Now, to show an implication, remember, you get to assume that all these things are true. So you know how in ordinary induction we say assume Pn is true and you're going to prove Pn plus 1? In strong induction, you get to say assume Pn is true, Pn minus 1 is true, dot, 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 P1 is true, and P0 is true. You get to assume a lot more. So it's a stronger proof technique because it allows you to do more, or so you would think. Now, in fact, any proof you can do with strong induction, you can do with ordinary induction. It just might be harder. So you can't prove any more with it, but it makes your proofs much easier, and we're going to do an example in a minute where the proof is much easier by getting to assume all of these things are true in order to prove Pn plus 1. Are there any questions about the difference here with strong induction? That now you get to assume all these are true as part of the inductive step? All right. All right, our first example with strong induction is going to be a simple game. We got a stack of 8 blocks here. Now, in this game, what you're going to do is divide the stack into 2 substacks. So I just took 8 and split it into 3 and 5. For that move, you get 15 points, 3 times 5. Let's write that down. Okay, so this will be, it's called the unstacking game. And in the first move, we went 8 split to 5 and 3, and that's worth 15 points. Now, in the next move, I'm going to split the stack of 5 into 4 and 1. And for that, you get 4 points, 4 times 1. And I keep on going until I have 8 stacks of height 1. And the last move, I'll be splitting a 2 into 2 1s. That'll give me 1 point. Then I add up all the points, and that's your score. And the goal is to get the most number of points when you add up the entire score. Now, just so this game is clear, we're going to play it. And I'm going to raise the stakes here. What we're going to do is we're going to have a competition between 3 members of the class and the TAs. Now, if the class team wins, they get more points, we're going to give everybody in the class candy. And I got lots of candy here. If the TAs beat you, they get the candy. We'll figure that out. All right, we'll come to that later. But you want to win this thing. All right, so I need some volunteers for the class who think they can do well. Yeah? Come on down. All right, you 2 guys, come on down. All right, TAs, come on up. Now, I want you to make some noise if you think your 3 class reps here can beat the TAs. All right. How many people? Make some noise if you think the TAs are going to win. Ooh, that's nasty. It must have been a rough recitation last week on Wednesday. I don't know. All right, so let's see. I think we're going to let the class go first. This is your stack. Now, think about what move you want to make first, because that matters. And you guys can give them some advice if you want as to the move they should make first. And then I'm going to keep score over here. Oh, OK. They went for the maximum move. That's good. They realized 4 times 4 is 16. Very good. So let's write that up here. You're off to a good start. In fact, that's the maximum number of points for the first move, I think. Good job. All right, so here's the class here. And here are the TAs. And the class went 8 into 4 by 4. And they got 16. The TAs are working hard here, as you can see. And they've got to move. That's a pretty pathetic first move for the TAs. Looking good for the candy for you guys. They got 7 points for the TAs. Class, what would you like to do for your next move? You can't start over now. Too late for that. A lot of people counting on you guys. No. Well, one at a time. No, just one. One stack gets split. Either one. There you go. Oh, well, what are you going to do now? The TAs are convinced they're going to lose. 3 and 1. Okay, good. All right. Interesting. So we got 3 and 1. That gives you 3 points. All right, TAs, we need to move. All right, so they've gone 6 and 1, 6 points. Class. You think you're dead already, huh? So you've gotten 3 and 1 now, again, for 3. So you're up to 22. You're way ahead, 22 to 13. All right, TAs. They look a little disorganized to me. What do you think? Another one. You can tell where they're headed here. 5 and 1. They got 5 points. They're up to 18. They're 4 behind you. All right, class. All right. You got 2 points. TAs. You really think they know how to do this best? I don't know. Oh, big change in strategy there, yeah. All right. Why? All that thinking, and that's what we got. Okay. 4 points. Class. All right, they pick up 2 more here. The 3 just got split into 2 and 1 for 2 points. How are you doing? You got 19, 22, 24, up to 26. 13, 18, 22. You're still doing good. TAs are behind. Let's see what they got up their sleeve here. All right, they definitely have a strategy going here. That's 3 points. There's not much option left for you guys. Yeah? Choose the right. Yeah. No. That'll be a 0. All right, that gave you a point. 2 went to 1 and 1, 1 point. Not a lot of choice for you guys either, I guess. There's only one way to split that stack. All right, 2 points. And your final move for the class and all the candy, you get 1 more point. Let's see what your total is. You got 22, 24, 26, 27, 28. And the TAs are going to get one last move for the TAs. All right, and you got 2, 1, 1, 2. Oh, that's interesting. 1, 2, 3, 4, 5, 6, 7. What else? 7 times 8 over 2. 50. No, that's not right. Did I do that right? Oh, 28. We got a tie. Ah, geez. All right. I tell you what, I'll give you guys one more chance to start over. You've seen that. You got to beat them. You tied them. You got to beat them. One more chance here. You got to beat them, though. You got 28. You already tied them. They came from behind and tied you. You got to beat them. You got off to a good start, but then they caught up. Oh, now your class reps had an interesting thought here. They ask, is it possible that any strategy gives 28? I wouldn't do that to you, would I? Yeah, probably. Any ideas? Can you beat 28? They're already eating the candy. In fact, you can't beat 28, and you can't do worse than 28 either, because every strategy gives 28. So I guess we're going to have to throw it to the class to vote who should get the candy. So if you think your reps really should win this and you should get the candy, make some noise. If you think your TAs should get the candy, make some noise. All right, so you get the candy, so why don't we, here, help pass out the candy here. We got plenty of bags and baskets. Take it all up on both sides and pass it out. Okay, is everybody getting some candy up there? We should have enough for everybody unless somebody got really hungry down here in front. Okay, so while you're doing that, let's try to prove this theorem. So the theorem is that all strategies for the n-block game produce the same score. It wasn't a coincidence for 8. And the score, we'll call it S of n for the n-block game. So for example, we're going to try to show that S of 8 was 28. So what strategy do you think we're going to use for the proof? Strong induction. So we want to write that down, proof by strong induction. What's the next step in a proof by any kind of induction? Base case, not yet. The predicate. What's the predicate here? All right, so, the inductive hypothesis, the predicate. Any guesses as to what P of n is going to be? What's that? Yeah, but that's part of it, but we're going to use this as a predicate to start with. You've gone a step ahead there. So I'm going to start with this as being the predicate, because I'm trying to show they're all the same, and I haven't figured out what the score is going to be, but I think you're already on a good track here for what the score is going to be. Now we do the base case. So we take n equals 1, the 1 block game. S of 1 is 0. We never took a move. We never got a score. There was only 1 block. We ended before we started. So that's OK. And now we have the inductive step. And here we get to assume P1, P2, all the way up to Pn to prove Pn plus 1. And so now we look at n plus 1 blocks, because that's where we're starting. So we have n plus 1, and we split it somehow. And it could be any split. We might have k on one side, and then n plus 1 minus k on the other side for any k between 1 and n. And let's figure out our score for that scenario. Well, we get the product of these numbers for the first step. We get k times n plus 1 minus k for the first step. And then as we recurse and we split up that block of k blocks, how many points do we get for splitting that all the way down? P of k, because that's the induction. We can assume that as part of the induction hypothesis. And how much points do we get for splitting this stack all the way down? Yeah, P of n plus 1 minus k. And do you see why strong induction is coming in handy here? For the TA strategy, k would be 1. We know P of 1 is 0. And you would just need ordinary induction. This would be P of n. But for a general strategy, it could be any split. So we need to have all these assumed here. Makes it much easier when you're using strong induction. All right, so this is our total score for the game for n plus 1 blocks. And we're trying to show it doesn't depend, it just depends on n. And then it doesn't depend on k. Does that depend on k? Well, it looks like it to me, right? I got k in every single term. So I'm not there. I'm stuck. You see why I'm stuck? Because I'd like to be able to say that the score I get for the n plus 1 block game, this is Sn plus 1, is the same for any sequence of moves. It doesn't even depend on k. But I can't do that. What do you do when you're stuck with an induction proof? What's one of the tricks?
Make it stronger.
Make it stronger, which means I get a stronger induction hypothesis. Now, somebody gave me one up there before. How could I strengthen my induction hypothesis here? Give the formula for Sn. That would make it stronger. I tell you what it is. What's a good guess for the formula here? Factorial. Well, is S of 8 factorial? Nah, not so good. Yeah, that's a better guess. Equals n times n minus 1 over 2. And in fact, what 8 times 7 over 2 is 28. It works here. Let's check another one. What's S of 2? 1. Well, 2 times 1 over 2. Ooh, it works. What's S of 3? 2 the first move, then 1 more. It's 3. 3 times 2 over 2 is 3. Ooh, it looks good. So now I've got a stronger induction hypothesis. Not only is it always the same, it is that number is your score. Let's see if that works. Let's plug that in now. So base case, let's check it out, is 1 times 1 minus 1 over 2 equal to 0? Yes. All right, let's plug it in here now. Well, P of k would be now k minus 1 over 2. This would be n plus 1 minus k, n minus k over 2, plus this one here. All right, I got to add all these things up and see if it equals that expression for n plus 1. Let's do that. All right, I get 2kn plus 2k minus 2k squared. I'm putting all this over 2. One giant mess over 2 here. plus k squared minus k, yikes, plus n squared. Well, let's write it just as n plus 1 times n. All right, minus kn minus k minus kn, all over 2. And now let's cancel. 2 kn's here, cancel kn, kn. 2k cancels k and k. 2k squared, minus 2k squared cancels k squared. Oh, and I forgot plus a k squared from here and here. So I'm left with n plus 1 times n over 2. That is Sn plus 1. And the k disappears. We've established now the stronger induction hypothesis. So not only did we prove that every set of unstackings gives you the same score, we proved the score is, for n blocks, n times n minus 1 over 2. All right? Oh, that's pretty good for strong induction. Lets you do some pretty powerful things. OK, very good. That's it for today.